Let me just share my screen. One moment. Give me one moment. I think I'll join from a different browser. My screen share isn't working.
Yeah, it's okay.
Yeah, sorry about. Okay, can I get a confirmation whether the screen is visible? Or is it showing the first? Okay, wait. I think it's showing the wrong one. Okay, that's better. I think it's visible now. Can I get a confirmation?
Yeah, it's visible.
Wonderful. So I'll just give a brief overview of like what we will cover and what to expect for the session. So basically, I'll be talking a lot about how I'll be focusing a lot on the side of competitive programming, and I'll be focusing on like the math behind certain problems and how to take a mathematical approach to solving all problems. So not necessarily all algorithmic all competitive programming problems have like a mathematical basis, but a lot of them do have a mathematical basis to them. So if you have an idea about that, then it makes it easier to recognize the kind of problems there are and to solve them. I think this session is open to like everyone from uni and just about to go to uni. I'm not too sure, but I tried to keep the requirements very basic. You have to be a little bit familiar with big O notation. You can search it. It's a simple concept. So it's a constraint that you can use to determine how much time or how much space an algorithm will take. So O of n means that basically the time that an algorithm takes to run is scaled by a factor of n as n becomes large, like very large. Other than that, I've written most of the code in pseudocode, so I don't expect you to be familiar with any language. Yeah, I think that's about all the basics you need to understand what we're covering in the session. So if you aren't familiar, just take a quick Google search. It's a fairly simple concept. So again, what I said is we have contest problems that come in many different ways. So sometimes there is a story about, there's a shark counting fish, there's a knight on chessboard, there are 10 mountains in a grid, there's a wizard casting spells, whatever. They usually like to put a fancy story away to like sort of cover the core of the question. So if you can read through that story and see what the actual mathematical object, the model there is with the question attached, then you can figure out how to approach solving that problem. So one thing when it comes to pretty much, I'm not sure if there are exceptions, but one thing when it comes to most competitive programming problems is there is a brute force solution. So what is a brute force solution? You compute every single possibility, you search the entire set of possibilities, and you find a solution. So, I mean, this is the very first thought that can come to your mind, like even a small child can figure it out. So if I have to find the maximum in a sorted list, I can go through every item in the list and find the maximum. So I have looked at everything. That is brute force, looking at everything. So sometimes maybe for easy problems, a brute force approach might be fine. But for more medium or difficult questions, typically brute force doesn't work. So how people constrain this is usually when in a competitive programming competition, you have some restrictions. So they generally give you have to run your code in 5 seconds or 10 seconds or something, or you can't take more than 2 megabytes of memory to compute this. So generally, when people are making a competitive programming problem, they will narrow down the constraints so that only the kind of solution, the optimum efficient solution that they're expecting can satisfy those time or space constraints. So that is why brute force doesn't generally work. But still, brute force is a very good way to get an idea of what the problem is about. So then what is the gap between a brute force solution and the expected, better, efficient solution? So the gap is finding some sort of structure. Maybe there's some periodicity, some symmetry, there's an invariant, there's some way of calculating it faster than going one by one. So that is what we want to find in a problem to solve it in the better way. So just to give some context about like the runtime. So in like the typical runners that they use for a competitive programming exercise, maybe if you have like the newest laptops, it's probably fast and can run more operations. But for what they typically run, you can do about 10 to the power 8 or 10 to the power 9 simple operations in C++. And maybe 10 to the power 7 in Python. Maybe that's becoming more with like newer versions of Python. And also you want to keep in mind that this is the biggest 64-bit integer that can be held. So these three numbers are very important when you are programming a solution to a problem. So basically an algorithm is not just is slow, fast relative to the input bound that the person making the problem chose. So basically you can like estimate your operation count. So maybe you don't need to do this. You can, let's say you have a loop or something and you do something inside the loop. So with that, try to estimate where you are. So sometimes in competitions, they give more time for Python solutions. Other times you have to use something like PyPy, or they allow you to use NumPy or whatever to match this. But for the purpose of the discussion, we'll just concentrate on this C++ estimate. So if your solution is roughly in this ballpark, maybe, but it's still not working for a few things, maybe you can optimize it a bit. You can reduce the operations within the loop or something. But if you are over by a factor of 10 to the power 3 or something, then your solution is not fast enough. It's not efficient, optimized enough. It's a brute force, or maybe it's slightly better than brute force. But the person who made the problem had a much faster solution to it. So then you can't pass the test cases for that problem, because the test cases expect you to run in a time that your algorithm simply can't run. So then you must find a better, more clever, more efficient, more optimal algorithm to solve the problem. So for the rest of the session, we'll go over like different ways where we can use mathematics to improve solutions starting from brute to something far more optimal. Sorry. Yeah. So basically, people will tell you that a lot of problems you will have, some statement, and there will be some number n for which you have to calculate something, and they will give you a bound. They will say, okay, n is greater than 0 and less than or equal to some amount. So based on that amount, you can figure out. So this is not a hard and rigorous constraint. There might be exceptions, but generally you can figure out the intended complexity of the solution. If it's a very tiny number like this, you can probably go into very complex solutions. So here it's probably some very complex algorithmic thing that you have to do. But by the time you come to bigger and bigger numbers of n, you expect the time complexity of the algorithm to become lower. So here, if n is 100, you can afford to do O(n to the power 4 time complexity. You can have 4 nested loops. If it's like 500, you can afford to do O(n cube). So there are some algorithms like Floyd-Warshall or some matrix multiplication algorithms you can find on the internet, which are, in this time complexity. Or if n is less than or equal to 5,000, big of n squared. If n is somewhere 10 to the 5, 10 to the power 6 range, you want at least a big of n log n. So maybe you want to do some sorting algorithm and then follow up with a simple loop, or use a segment tree, a sieve, or method where you have 2 pointers, where you can avoid O(n) square by having like a smaller loop within a larger loop, or something like that. If it's 10 to the power 7 to 10 to the power 8, then you want at best a solution of big of n, so only one loop, nothing complex, no smaller loops or anything within that. And if n is less than 10 to the power 18, that means probably there is going to be some very intense mathematical manipulations there. you are supposed to either get it in O of 1, or maybe at best a simple algorithm with a small compressed loop of log n. So there may be fast exponentiation, some mathematical thing, or some other clever manipulation you will have to do. So if you're doing practice problems on there's like 100 platforms, HackerRank, LeetCode, Code Forces, whatever it is. So look at some problems and you will see a lot of problems will have some constraint, some bound for the size of the input. So then either solve them, or you can look up the editorials or the discussions or solutions or whatever there is, and you will generally see that the expected solutions time complexity aligns like this. So take a look, and if you are ever struggling with a solution, your solution is not passing the test cases because they are timing out, then know that probably if your solution isn't the correct time complexity, it's probably not the best solution. So something to keep in mind. So like I said, first figure out the brute force solution. It doesn't matter if it's probably not going to be the solution that works, but it doesn't matter. It gives you a good idea of what the problem is and how to approach it. And also, if you want to test a different solution, you can see if it is correct using the brute force approach on your own laptop. And then you check the complexity and you figure out how much of a difference there is between brute force and the expected complexity. And then you can look into other things like, okay, what am I recomputing? Are you doing the same calculation again and again? So then you can maybe cache it. You can use dynamic programming. If there are quantities that never change, you can look at invariants. So this is where like you can take a mathematical approach, and you will offer, if you solve a lot of problems, you will see some patterns. So, and you will see like certain ways to solve those patterns. So if there is something saying, give me the solution, modulo 10 to the power 9 plus 7, you'll see that commonly. Or is something possible to be reached, or what is the expected value? Then there are typical approaches you take for those kind of solutions, problems. So then it becomes a matter of identifying what kind of problem it is. So we'll look at some of those different types of problems. So first we'll take a look at modular arithmetic. So I forgot to mention this at the beginning, but again, I assume you have some basic knowledge about things like modular arithmetic. I think you had modular arithmetic in high school, if there are any people who have not reached university yet. So this is where A is congruent, B mod C, where C is the remainder where you get by dividing something by something. So if you're not familiar, just do a Google search of what modular arithmetic is. It's a fairly simple concept. So if you do especially a lot of counting problems, count how many such things are there, count the number of combinations, count this, count that problems, you will see a lot of them ask you to give the solution modulo this number or this number. So these are not randomly chosen numbers. They're chosen because they are very large prime numbers, and they are also 64-bit integer. They're like 64-bit integers. So they're like some of the largest numbers that a computer memory can hold, and they are primes. So that means you're probably going to be working with massive numbers, or rather the answer, not the solution, like the count involved in the problem is massive. It's probably something you can't possibly write down. It has more than 64 digits. So then you have to think about it, unless like there are one or two problems which do actually test your big integer computations, which are incidentally generally easy questions. But yeah, unless the person making the problem wants to test your big integer library, which they probably don't want to, they just want to test not whether you found the exact number of the right count, but the method to find the right count. So they ask for the answer modulo a prime. So they ask it that so that it's a big enough that collisions with incorrect answers are not a problem, and small enough that the product fits into 64 bits, which is the largest integer in memory a modern computer, I mean most used modern computers can have. So then that's something to keep in mind. So just because it's mod p doesn't mean that the counting is easier. You still have to do the combinatorics or whatever it is. But mod p makes the answer fit in memory. So that's why you will see these two numbers in a lot of these counting like questions. So something to keep in mind, the modulus operation, so a plus is compatible with addition, subtraction, and multiplication, but not with division. So you can see a plus b mod m is a mod m plus b mod m and mod of m. So in case this is bigger than m. So likewise, multiplication also similar. So this means you can reduce at every single step instead of the end. So that means instead of getting a massive number which you can't hold in an integer or which will overflow or something and give you either space memory or the wrong number, you can reduce it after every multiplication to a number that can still be held in memory without problems. So if the constraint is a is less than 10, a and b are both less than 10 to the power n, then a times b is less than 10 to the power 18. Okay, it can fit. Now then you multiply it again, it doesn't. So you have to sometimes you have to reduce after every multiplication, that is get this final value, so that something doesn't overflow. And some considerations in some languages like C++ or Java, sometimes the modulus is kept negative if you have like a negative number. So that's something to keep in mind. And again, remember division, you can't do like you do multiplication over here. So it's, for a lot of these problems, you can use some helper functions to add, subtract, and multiply these. So then, sorry, give me a moment. So then something we are going to look at is fast exponentiation. So then if you are computing something modulo, big number, so let's say you are computing a to the power b mod m with b constraint up to 10 to the power 18. So it's a very big number. So if we are multiplying a b times, then that is big of b, which is 10 to the power 18, which is way out of our time complexity. And then if you are squaring this, it becomes big of log b. So now that's like exponentially smaller. So then what we can do in this case, it's fairly simple. We work with exponentiation. So what does that mean? So if we have to compute a to the power 13, we compute it as a to the power 8 times a to the power 4 times a to the power 1 mod 13. So basically these are just powers of 2. So we break this down like that. And then what we can do is we can use modem to calculate what we want with a simple pseudocode like this. Here, what we do is, sorry about that. What we do is we start with A and we set the start to 1 and take A is A modem, and while B is greater than 0, if B is odd, we push it by 1 so that B becomes even, and then we make A square modem and B we divide by 2. So now we went from A to the power 8 times A to the power 4, and we only had to do one calculation, which is find the modulus A square. So like that, you can use exponentiation to greatly reduce the number of steps. So in this case, by a factor of log B starting from B. So then you can solve the problem within the given time complexity. So this is very simple one. There are much more complicated sounding problems where you have to figure out how to transform the question into this form. But if you do enough, if you go through all these programming websites, you will eventually find some problems of this form. And then again, you have some periodic or cyclical things when it comes to modular. So for any fixed A modulo M, the powers of that, so like a to the power 1, a to the power 2 till a to the power whatever, must eventually repeat. Because why? I don't know if you are familiar with the pigeonhole principle. So it's something a little bit like it. Because there are only M possible values modulo M. So it can only be 0, 1, 2, 3, M minus 1 modulo M. So if you have more than M powers of A, then it will definitely repeat at that point. So it can repeat way before that. But the point is that it will eventually repeat. So for example, with the powers of 2, you take 2 mod 10, you will see the last digit is always 2486, 2486. So there is a repetition. So related to that, there are 2 theorems that you can look up, maybe search it and see what they state. So this is Fermat's little theorem. This is the easier of the 2 and more commonly used, which states a to the power p minus 1 is congruent 1 mod p, where p is a prime and the greatest common divisor of a and p is 1. This is Fermat's little theorem. So you can use this to reduce exponents mod p minus 1. So likewise, this is called this weird symbol is Euler's torsion function, which is the count of all co-prime numbers less than n. You can look that up if you're interested. But again, what you can ultimately use this theorem is to find a cycle. And when you find a cycle, a massive problem becomes very simple. So if you want to find 2 to the power, I don't know what is this, 1 million, I think, whatever, to the power 1 million mod 10, then you can reduce this problem greatly. What is this? 10 to the power 6 mod 4 is 0. So then fourth element is this. Why? Because it always has a period of 4. So likewise, if you can, if it's a obvious period, you don't need any of this nonsense. You can just write down the first few values and see if something is cyclical. and then reduce that. And otherwise, you can use these theorems to find a period, and then it's just a matter of dividing the big number by the period length and figuring out which position in that the cycle is the big number. So that's one way you can use modular arithmetic to solve big calculations like that, like finding this. So then another thing is modular inversion, where so earlier we talked about how what did I do? Sorry. Where I said, look here, you can do plus minus multiplication, but not division. Then how can we do division with modular arithmetic? So we want a number that behaves like 1 over b. So then we define b inverse as the value with b times b inverse is congruent 1 mod m. So then divide by b means multiply by b inverse. Then so this is just some random number. We don't know what that number is still. Then from Fermat's little theorem, the one we looked at earlier, this one, you get b inverse is congruent b to the power p minus 2 mod p, where p is prime and b and p are coprimes. So then we can find one of this thing we get when dividing by b. So we essentially figure out a way to get the value modulo p when dividing by b without actually doing the division. So I'll be sharing the slide decks later, so there are some like conditions and explanations as to why this always exists and whatnot. You can look at those later if you are interested, but for now just keep in mind that this is something that you can do. So if we look at a problem like this, Nestor's maths teacher gives him two numbers, a and b. Find the last digit of a to the power b. So a is less than or equal to 20. Okay, that's fine. B is less than or equal, I don't know what this huge number is, and there are 30 test cases. So this is what is this? 2 to the power 2 times 10 to the power 9. 1 to the, yeah, so this is of the order of 10 to the power 9. 2 times 10 to the power 9. And if you look at the number of test cases and this, you will see probably not going to run very fast if you want to loop over everything. So the brute force solution is you want to compute a to the power b and take the last digit. So 20 to the power 2 times 10 to the power 9 is, or rather this number, 20 to the power this number, and there is over 2 billion digits. So even if it was possible, it would be extremely slow and we would be way over the time complexity allowed, but it's not even possible because our memory can't handle integers this big. So then the brute force solution is not going to work. So then we obviously use, you know what last digit means, modulo 10. So we reduce as we go. So now it is solvable, but we are still not within the time complexity if we are going to keep multiplying. So then what's next? We can use fast exponential modulo 10, which we looked at earlier. So we can write an algorithm like that, and that will get us to log n time. So log n for this log n of this, I don't know what that is close to. It's probably still a very big number, so it might work, might not work, or we might be able to exploit a cycle. So a is less than or equal to 20, so maybe there is some cycle. So maybe the answer is a to the power b mod 4 if there is like a period. So then we look at like a is a very small space. So depending on that, we can figure out how to make a solution that is either O of log b or of 1. So then the whole problem was this figuring out that this problem. So I mean, this one is fairly simply worded. It says Nestor's math teacher gives him 2 numbers, but sometimes they might throw some big story about, I don't know, a magician and a rabbit and something and throw you off. So figuring out that this is a modular arithmetic question is the first part of the solution. So then you can figure out how to, calculate this in a time efficient way that doesn't violate the time constraints you have in big O. So then something to consider. Sometimes you have these questions where they want you to calculate something for m queries. So that is, they're asking you to make a calculation and they're telling you in the test case, they're going to ask the same question but for different values m number of times. So in problems like this, what you might want to do is sometimes you can pre-compute something and use that value. So here is something that happens in many places, not always a problem. NCK, this is how to choose. I'm not sure if you're familiar with this particular notation. It's how many k you can choose from this. So how many k you can choose from n values. So this is generally written as n factorial over k factorial times n minus k factorial. So if you want to calculate this once, okay, maybe you can do that. But if they are asking you to calculate for 1 million queries for different n and maybe k, then that time complexity is going to balloon. So what you do is, we do one big O of n pass up front to calculate 1 factorial value, and then we use that to answer every single query afterwards, which turns every query after the first one into big O of n, big O of 1, or rather constant time. Here is some pseudocode to do that. And you can see how we have this backwards loop. You have a factorial of nk is like reduced in this particular manner. So you can take a look at the pseudocode later once I share this thing. But for now, know that you can do pre-computation like that when you're answering a problem with multiple queries. So that's a few questions from modular arithmetic. Next, we'll move on to another mathematical concept, which is parity and invariance. So typically, you have questions asking, is something possible, yes or not? So obviously, if you can again compute the entire search space, brute force, and find out whether something is possible or not, but that's very time consuming. The alternative is to find some condition that tells you this is impossible without having to do any calculations or computations. So typically in problems where they ask you something, whether something is possible or not, you can look for parity or invariance. I mean, parity is also an invariant. So for example, sometimes you have this problem, there are two players and these are the legal moves. Every player makes a move. At the end, which player is going to win if we start like this or something like that. So then in that case, an invariant is something that a legal move doesn't change. So if this invariant then at the start is different from the invariant at the target or the end which they are asking, that means you can't go from the start to the end because the invariant doesn't change no matter what you do, but the invariant is different from the start and the end. So that means it's impossible. So typically, not all problems that have wording like this necessarily involve an invariant, but typically if they ask, is it possible to do something? Can you reach this particular game or state? Can you reach this place using these moves? Determine whether this sort of number is possible. And there is like a massive number of possible moves. Then it's probably something involving an invariant. So again, brute force is very bad here. And typically you look for maybe a sum, modulo something, a count, so of everything on a set, or if it's like a chessboard or some sort of dominoes problem, maybe the color of a square or the number of inversions and a permutation or something like that. So very simple thing sometimes, probably not found often in difficult problems, but sometimes even in medium problems, something to look is whether, even plus even is even, odd plus odd is even, or remember this parity. So it's the simplest invariant possible and it's there in some problems. So then this is relevant if you notice that an answer depends only on the parity of something, not its value. So somebody is asking about the largest odd sum or the largest even sum, then you can look for parity. And then other things are like coloring a chessboard. So a knight's move always changes color, domino always covers one of each. So to cut two same colored squares from a board, it can no longer be covered by dominoes. So things like that, you can look for an invariant of parity. So one problem is finding the maximum even sum. So if you are given n integers and you can use each integer at most once to obtain the maximum possible even sum. You can use none of the integers if you want, giving a sum of 0. And there are 1 is less than, n is less than 100,000 integers, and each one is in the range 1 and 10 to the power 9. So if you are going to try every subset, the brute force approach, which is kind of ridiculous here, you get big O of 2 to the power n. And 2 to the power 100,000, I have no idea, that's a ridiculously large number. So it's probably not something you want to even bother trying. So then they have given that all numbers are in the range 1, 10 to the power 9. So that means everything is positive. So the bigger the subset, the better. So you can take the greedy answer, which is everything. But then we have a problem. What if the sum of everything is odd? And that's a problem. So then we realize, how do we make it even? We have to remove something. So if we remove even number, it doesn't change anything. So that means we have to remove only the odd elements. Then which odd elements do we remove to get the maximum even sum? So to get the maximum, we remove only one odd number and we have to find the smallest odd number. So then what do? We can do a simple loop big O of n, and while we do that loop, we keep track of a sum and the smallest odd number. And then if the sum is even, okay, great, we don't need to do anything. If the sum is odd, we track the smallest odd number and we reduce that. So then it's a big O of n. So simple solution. So another similar problem. So it's 6:20. I won't have time to be interactive, so you just think about it while I speak out loud. So there are 23 coins lying on a table. Exactly 7 of these coins show heads. A move consists of flipping any 2 coins. So you can pick any 2 coins and flip them. Can you reach a state where all 23 coins show heads? So then, while the invariant here, number of heads is odd. So any move flips 2 coins. So either you flip 2 heads, 2 tails, or head and a tail, which means the head count changes by 2, 0, minus 2. Always even. So that means the number of heads being odd is an invariant. Therefore, the target 23 heads is also odd, so it's not excluded by our invariant. So actually for this one, it's actually reachable. But one thing to keep in mind is that just because the invariant holds doesn't mean it's always reachable. So that is something to keep in mind. Just because 23 is odd and 7 is odd doesn't mean that we can reach it always. However, if we slightly change the problem, we say 8 heads are there, and now we know that it's impossible. So typically an invariant will not necessarily show that something is possible, but it will definitely show if something is not possible. So keep that in mind. Sometimes it gets a little tricky. You might have to have some extra conditions in addition to the invariant to figure out if something is possible. Or sometimes the person who made the problem is a little tricky and he will put the big problems with an invariant. But the cases where it's impossible with massive calculations and the cases where it's possible with tiny calculations. So sometimes that is also a possibility. So anyways, keep in mind, you can use an invariant to show that something is impossible, but generally it's more difficult to show that something is possible just because it satisfies the invariance condition at both the start and the end. Let's take a moment. Next, we will look at some number theory. It's 6:30. We have some time. So next, typically you have a lot of problems you can work with, like things like the greatest common divider or the least common multiple. So then something to keep in mind is that the GCD of A comma B is equal to the greatest common divisor of B and A mod B. Why is this? Because if this divides A and B, it also divides A minus something times B, and you can use this relation to simplify calculation. How you find GCD A comma B while B is greater than while B is not equal to 0, 1, whatever. You turn A to B, assuming B is the smaller number, A to B, and B to A mod B. And eventually when it stops, you return A, which is the GCD. So likewise, the least common multiple is also A comma B is A over GCD AB times B, but you can't use modular arithmetic because you can't directly use modular arithmetic there, and something to keep in mind is sometimes this can overflow. But the fact of the matter is, you can use a relation like this to compute this without going into a big loop. So here, minimum of, let's assume b is the small number. Then you can find the greatest common divisor in big O of log b instead of being big O of b ab, where you, sorry, no, not ab, big O of the larger one of a or b, in which case you just loop across everything. And 6:30. So I'll skip this part, but there are like some extensions of Euclid's algorithm. Typically, maybe if you are interested, take a look at the Chinese remainder theorem. I've seen quite some problems with the Chinese remainder theorem. These are less common. Next, again, another technique is the sieve of Eratosthenes. So this is for prime number calculation. And what is relevant here is, so obviously you can have like to see if some number is prime, you can you can try to divide it by every single number up to n, which is, for a single number it becomes O of n, and if you're trying to fill an array, that becomes almost O of n squared, or rather O. Yeah. So what then you do is, instead, to find if n is prime, we check for I in 2 to square root of n. Why we do that is, if n is not prime, then for every divisor larger than the square root, there is probably a corresponding factor which is smaller than the square root. So you will find that. And if n is actually prime, then there will be no factors above square root of n. So basically, any factor above square root of n will have a corresponding factor less than the square root of n. So, and so then you can use a simple loop, actually nested loop here. So 1 to square root n, you do this for j in whatever value up to n, and you will see that that becomes the log of log n. So you know that this is like log of log n because we are using the square root over here. So that means it's almost like very fast compared to going through loops for everything. So that is something you want to keep in mind if you are doing a prime number, if you are checking if something is a prime number. So just keep this in mind. So look at this, it's a very, very common thing. So you keep this in mind if you are going to calculate anything. So if you are going to calculate for this, the time complexity becomes log O(n), log of log n, which is almost constant. So it becomes O of n. So then again, something similar, O, the smallest prime factor. So here we keep an array again. So here we put an array for everything from 0 to n. So here, instead of seeing whether something is prime, we store the smallest prime that divides it. And then with factorize, basically we just go ahead and fill this up. And again, for the loop, we have the same condition. We divide by whatever numbers up to the square root of n. So that is the largest optimization, and there are a few other optimizations like this. We start here and we stop where. So just look into those. Keep in mind that if you want to do something like find out if, especially if there's more than one number and they're asking you, yeah, we give you multiple numbers and you have to find out if each one is prime, then you should do something like this. And same for if they ask for the smallest prime factor or something like that. I will skip this for the time being since we are running a little late. Next, counting divisors of a number 100,000 times. So you are given 10 integers. For each, report how many divisors or factors that it has. And here, 1 is less than or equal to n is less than or equal to 10 to the power 5. And also 1 is less than or equal to xi is less than or equal to 10 to the power 6 is the number of these things. So what matters is when the same question is asked many times over a bounded domain, stop answering questions and start filling a table. So that means if there is something you have to calculate the same thing twice when they are asking the same question n number of times. So in this case, for every xi, which is in this range, they ask you how many divisors it has. And that means if there are 10 to the power 5 in this range, it's probably going to be a lot of overlap. So then to prevent recomputing during that overlap, you can fill a table so that if it's already in the table, you can just take it without calculating again. So the brute force approach is every query. So for every one of these n integers, you divide by every number up to root x until you can factorize it. And you can get up to like 10 to the power 3 times there are 10 to the power 5 questions asked. 10 to the power 3 because this is 10 to the power 6, so square root becomes 10 to the power 3. So roughly you get 10 to the power 8 operations. It's very tight, and depending on the person who made the problem, they will probably have set a time limit, which is not enough for you to run this in. So then what you realize is domain is small and shared. Every query is an integer below 10 to the power 6. So there are only 10 to the power 6 possible questions. So this is much less than all of this work. And then what you can do is you see the divisor counts for everything at once. For each d1 to 10 to the power 6, you work multiples and increment their counter. So what you do is you loop across 1 to n, and for m in d, 2d up to 3d or up to whatever the largest multiple of d is less than n, you increase the divisor count by 1. So now we turn this from big O of n root x, where x is this massive number, into something which is O of n log n. So this inside one, these are multiples. So this becomes n over m, which is roughly, when increasing, it becomes log of n. So there you can compute a table of results in this time complexity, and then everything afterwards you just look at the table and you give in constant time the answer. So pre-computation like that is also a very important thing. I keep doing that, sorry, my bad. Okay. We have a couple more sections. I will try to finish it in the next half hour, so that we'll have a little time for questions also. So next, combinatorics is counting without enumerating, finding number of combinations, whatever. So some typical identities which are very useful is that NCK, which is, again, I mentioned this earlier, n choose k number of ways to choose k from n, which is n factorial over k factorial times n minus k factorial. So this is a definition. And there are these two ways to resolve this, which is NCK is equal to n minus 1 ck plus n minus 1 k minus 1, which is Pascal's identity, which is useful if you are pre-computing something and you want, or if there's like a loop for something, it's useful. If you want, you can write this down and prove it yourselves. It's a simple proof. And the symmetry is that n choose k is the same as n choose n minus k by this definition. So you can use this to reduce the search space that you have for a particular problem. So if you're working with something where n is less than or equal 5,000 and there's a large amount of questions nk asked, you can create a table using Pascal, which gives O of n squared complexity. If n is less than or equal to 8 or 6, it's probably a big number, then you can use modular prime calculations and factorial times inverse factorial, whatever it is, to figure it out directly. If k is tiny and n is huge, you can use this. It's not worry about the other two situations. If you are interested, take a look at the Chinese remainder theorem again. I think I mentioned this earlier also, but I'm not going to go over it because it's a bit more complicated and we are running short of time. But sometimes for some problems, you can use the Chinese remainder theorem. I'm not sure why this keeps doing that. Okay, we are doing. So something again, way to, how do I put it? A way to turn a problem into a mathematical model. So I'm going to call this stars and bars. So this is draw n identical stars in a row. So like this. Insert k minus 1 bars to cut them into k groups. So now every arrangement of n stars and k minus 1 bars is exactly one solution. So we want to find out how many solutions are there. We count the number of arrangements. So for every bar, there is this many spaces. So then this becomes a combinatorics problem of n plus 1 minus n plus k minus 1. Choose k minus 1 positions to hold the bars. So this is like an oversimplified version, but you will find there are many problems with a lot of fancy descriptions that you can essentially reduce to a problem where you're dividing these stars into groups with k number of bars. So for that, if you can figure out that the problem is of that type, then you can use this simple identity to calculate what you want. So then again, something when it comes to counting type problems, if there is a problem that asks you how many satisfy this and it's some complex combination, or you feel like there's a lot to count, if you are counting how many satisfy a particular condition, you can try to find the complement of that, which is, okay, how many are there in total? How many don't satisfy this? If that is simpler, assuming it is simpler, it might not always be, then you can find the total, subtract how many fail, and you will get how many satisfy. So for example, paths avoiding cell X is all paths minus paths that go through cell X. So this is probably a much smaller number and easier to calculate. So things like that. And the similar thing comes when it goes to inclusion, exclusion. So I think everyone here probably has worked with sets. So you know that the size of A union B is equal to the A plus B minus size of A intersection B and all this stuff. So you can use these to figure out counts for things that are a little too complicated or too large to count directly. So one problem, this is probably going to be, I'll try to go through this one in detail and rush the rest because this is a very difficult problem. So you have a grid of H by W cells. A pawn starts top left and moves only right or down, aiming for the bottom right. So all the way from the top left, he wants to go to the bottom right. There are exactly K cells that are black and may not be entered. So they want you to count the valid paths, mod 10 to the power 9 plus 7. So here, H, W are less than or equal to 10 to the power 5, which means total number of cells is 10 to the, probably in the range of 10 to the power 10. This is massive, whereas K is fairly small. K is less than or equal 2000. So starting point might be, you might think we want to use dynamic programming and we use the identity there, paths ij equals paths I minus 1j plus paths I j minus 1 for all 10 to the power 10 cells. But then you have 10 to the power 10 cells, that's too much space complexity. And for calculating that, too much time complexity also. So this one is in the range of big O of 10 to the power H times W. So it's probably not something we can do. So in that case, we try to do DP, but we try to figure out something else. So we know we need to avoid just these 2000. So in that case, we do deep dynamic programming. Sorry, I don't think I went over dynamic programming. If you haven't already done like a programming course, maybe Google dynamic programming. It's a little more complicated, but still fairly straightforward thing you can learn. It's basically if I oversimplify it, it's basically caching what you already calculated and avoiding calculations sort of thing. Yeah, so basically what you want to do is you want to stop doing dynamic programming over the grid and instead do dynamic programming over the interesting cells, which in this case is just these 2000 cells. So unobstructed paths, we know from one cell to another cell is just a binomial. So you always go only right or down. So that means you can easily calculate the number of paths from one cell to another with simple mathematics. You don't need to count anything. You just have a simple formula because it's a only top. You can move right or down. So there's always two choices only. So then there's like a simple binomial this thing and you can pre-compute that. So as long as obstacles aren't there, you can simply use a formula for calculation. So then the obstacles are what's preventing. So what if you do complementary counting? That is all the paths from top left to bottom right minus paths that are going through a black cell. So then that is more calculatable. You just have to calculate for this K, big O of K times whatever it takes to calculate. But the problem there is a path through two black cells is removed twice. So then if you are going to do inclusion exclusion, so you get to about 2000 terms, which is again not doable. So then we try to figure out some factor which allows us to make it complementary, but without an inclusion exclusion problem. So then we classify each part by its first black cell. So now what we do is we saw the black cells, and we have parts reaching the black cell whose first black cell is I. And then we can just do a direct calculation. So then you get big O of k squared plus h plus w. So if you can just think about this, try this problem out. Maybe what I said might not have, I said a lot of stuff, so maybe it might not have gone to your head right now. And yeah, definitely look up what dynamic programming is also while you're at it and solve this problem. It will give you a good idea of how to, and if you I think this is some code force or something, so maybe I'll try to find the problem and share it. Otherwise you can just Google this. I think if you Google it, you'll find the question. So check like the discussions also, and you will get some idea about how to reduce the combinatorics problem to a simpler one. So that's a good thing to go through. Okay, I'm sorry. So it seems it keeps scrolling up. I think I put some nonsense CSS there. Yeah, so we'll skip this since we are running out of time. Probability and expectation. Again, if they're asking you to calculate expectations, you can keep in mind that expectation of x plus y is equal to the expectation of x and plus expectation of y. Blah blah blah. It's helpful because again, I hope you have like a basic idea of what an expectation is. If not, just do some introductory reading on probability and statistics, and you'll see what it is. And it's helpful because it lets you decompose a big quantity into easy pieces, which you can compute simply in isolation, and then you can just add it up. So whenever you are asked for the expected count of something, write the count as a sum of 0 or 1 variables, one per thing that might be count. So then you have expected count is the summation of probability event I happens for each event I. So then it's just a matter of looping this and adding. So we'll look at a problem. So you have a fair m-sided die with faces from 1 to m, and the m-sided die is thrown n times. So they're asking find the expected value of the maximum thrown. So here 1 is less than or equal m comma n less than or equal 10 to the power 5, and they want the answer as a real number. So it's an expected value. They want the float, or maybe they'll probably give you like a round, or if it's like a fraction, whatever. So then how do we find the expected value of the maximum thrown? So remember, this is the maximum, so it's not the average. So it's not m over 2. You actually have to do a big calculation there. So what is the brute force approach here? There are m to the power n sequences. So I mean, each throw can have m values, and there are n times of that. So it's m times m times m n times. So there are m to the power n sequences. So when m is equal to n is equal to 10 to the power 5, that's 10 to the power 5 to the power 10 to the power 5, which is too big to work with. So yeah, we can't even write it. We can't have it in computer memory. We can't possibly go through a loop of that in any time complexity that will allow us to calculate anything. So brute force is not an option. It's not a realistic option even with a supercomputer, I think. It's a big go of 10 to the power 5 to the power 10 to the power 5. So then what we do is we try to simplify this. So we simplify it like this. So max is less than or equal to k means every one of the n throws is less than or equal to k, and the throws are independent. So we first realize that the probability for maximum being less than or equal to k is equal to k over m to the power n. Why every one of the throws is less than or equal to k? So you have k possibilities out of n possibilities, and the probability of that happening is k over m for multiplied by each throw. Then we use this identity to figure out the event where the maximum is k. So probability of maximum being k is k over m to the power n minus, so this is maximum is less than k, which means for this we want maximum less than k minus probability of maximum less than or equal k minus 1. So, and that value according to this formula again is k minus 1 over m to the power n. So now we have a way to calculate the probability of the maximum being k. So then what do? We sum, we get the sum. So what is the sum over k for the probability of maximum being k? So then you have one loop over all m values, and for that you have to compute this term. So that is log of n, and because we are computing a power, so log of n is, as this is a fairly small, relatively small number, so this value is less than 10 to the power 9. So all in all, it becomes m log n, which is much better than this. So that is also something else that you can do in problems where they are asking for expected values. So we broke it down into events, and we broke the, for each event also, we broke it down into some sort of a difference, subtraction, not an addition, of two different events that are simpler to calculate directly. Dynamic programming for expectations, I think we'll skip this. I will give you these slides. I will share them with the organizers later. So if anybody is really interested, you can go through the slides later. Matrix exponentiation. Again, this is like something we can use to like iterate over recurrences, and we use some mathematics over here. I'll just skip this because again we are running late, but basically this is all ways to do fast exponentiation. So if you look at these algorithms, you say it is very similar algorithm to what we looked at in section 2 under fast exponentiation. So if you are interested, yeah, you can take a look at these, and I will bring the session to an end by reiterating what we wrote through. So at the beginning, I told you, in competitive programming, you want to look beyond the fancy problem statement with the wizards and the magic things and the space astronauts and the walks and cities, and figure out what is the actual mathematical model behind the question. So we found some recurring themes in questions and what to look at for all of those. There are some things we didn't actually go through. If you are feeling a little more advanced, I have highlighted a few other things that you can look into. These are like algorithms or specific functions that are also used. But what we covered is very good for you to get a good basis and solve at least most easy and medium problems. Yeah, so there's a lot of things we skipped. DP optimization, we didn't even look at DP. There are things as generating functions where we find a way to yeah, it's a bit complicated, but basically these are a few topics. If you are comfortable with everything we went over in the slides, these are a few topics you can search. And how to approach this is, first you can do a Google search, or today, I mean, you don't need to do a Google search. You can ask Cloud Code or ChatGPT or whatever it is that you use about this. And then you can search for some problems which are using this on HackerRank or LeetCode or Code4Serve, or whatever it is, the website that you like to do competitive programming practice problems on. Particularly interesting, something we didn't even touch on today, is computational geometry. So look at that, for example, as a beginning, and also look at something like Kirchhoff's theorem, because we didn't cover trees and stuff much either. So yeah, those are some good things to look for if you are comfortable with everything we covered today, some advanced things. So finally, I went through a lot of things. Some of it maybe went to your head, some of it didn't. It doesn't matter. You're probably not going to be able to look at a problem and figure out. I mean, you can probably figure it out if you take a lot of time, but in a competition, time is also limited. So you probably want to get a little bit of experience, see problems. So you want to look at some places. So you can look at the CSES problem set. There are 300 problems by topic, and you can start there. Or there are some other places. There's a Code4Serve problem set, which is filtered by tag and rating. And you can pick number theory or combinatorics and work there. Or if you're interested in mathematics first, programming second, look at Project Euler. It has a very mathematical set of programming problems. I think all of you will like it. I hope Project Euler is still around. I used to do this when I was in my after O-level, after A-level days, and I had free time. So I think all of you will like this. Do Project Euler. See how far you can get. Then there are some resources. I forgot to add here. For any basics that you are missing, if you aren't familiar with big O notation or dynamic programming or some class of algorithms, in addition to these, there is something called Introduction to Algorithms, big fat book you can hit someone with if you are angry after failing to solve a coding problem. But yeah, those are some good resources to get started with. And remember, always read the constraints, get an idea of the type complexity. If you can't figure out a solution, work with brute force and then figure out, are you recomputing something? Is there an invariant? Is there a simple way to optimize the brute force? And figure out what algorithms actually have underneath them, why they are used, what they assume, and how you can use them. So it's 7 o'clock. I think we have time for some questions if anybody has questions.